Hey, it is Mr. Shrum. How's it going? We are going to move on with motion, and today we're going to talk about measures of motion. So in this lesson, we're going to define distance, displacement, speed, velocity, and acceleration, and understand how they are related. Now, we discussed this a bit in the previous lesson. Here we're going to get a little deeper. So in the intro, Dave was excited. A horse that he'd been training just won its first race. The horse took only 2 minutes to travel around the 1.5-kilometer track. Dave was sure that he had a great racehorse with a bright future. His friend, a physicist with an annoying sense of humor, told Dave not to count his profits quite yet. The physicist said that the horse wasn't so great, having raced with an average velocity of 0 meters per second. Now Dave, who knew a bit of math, was outraged. He pointed out that the horse had run an average of 12.5 meters per second. The physicist smiled and said, "I'm still right." Think about the scenario for a moment. Is the physicist's friend right, or is Dave? So they are both correct. And in this lesson, we'll study the concepts of speed and velocity, as well as displacement and acceleration. And hopefully by the end of the lesson, you should be able to explain why they are both saying the correct thing. But first, let's talk about distance and displacement. A linear motion, whether it's a bike ride or a satellite launched into space, you can answer the questions like how far, in which direction, how fast, and is it slowing down, speeding up, or moving at a steady rate? We can answer all of these questions with measurements. So for the first question, how far? This is the distance covered by a moving object. So picture a car moving from point A to point B and then to C. So to find the total distance, we measure this distance and this distance, right? And that's it. No direction needed. It's just a scalar quantity with only a magnitude. And other scalar quantities are mass, area, volume, temperature, and speed. So it just tells you how far distance. Now let's see. If we needed to tell someone the final position of point C, we need to describe not how far, just how far away it is, but also in what direction it is in relation to this first point. And this change in position is called displacement. It's a measure of the shortest path between the initial point A and the final position, which is point C. Because displacement has both magnitude and direction, it's a vector. Other vector quantities, velocity, acceleration, and force. So we have distance, which is scalar, only the magnitude, and then displacement, which is distance plus direction. So let's look at an example to better understand the difference here. So we have Rita. She's starting at point A, right here. And she walks 100 meters east. So we're going this way. So that's here, 100 meters. Then she turns around and walks 50 meters back from where she started. So what are her total distance and displacement? Because distance is scalar, the direction, not important. No matter how many changes there are in direction, the distance is always the total length traveled. So she went 100 and then 50. So that's 100 plus 50, which is 150 meters for distance. But her displacement is the shortest path from point A to her final point. And that happens to be 50 meters east of A. Okay? So don't forget the direction. The shortest distance between A and the final point is displacement plus a direction. So 50 meters east. And then it says, imagine Rita starts from point A and walks a distance of 150 meters while changing direction several times before returning to her starting point. What is her total distance she covered? And what is her displacement? Her total distance would be 150 meters, and her displacement would be 0 because her final position is 0 meters away from her initial position. So if you leave this point, go back and forth, and then wind up right back where you started, you didn't change position between these 2 points in time. Since you winded right back where you started, your displacement is 0. I hope that's making sense. Here we're given a question. Jason rides his bicycle 1,200 meters east to the grocery store. He then turns around and travels 760 meters west to meet his friend. What are his total distance and his displacement? So, distance, we're just going to add these two up because it is a scalar quantity with only magnitude. And we have 1,960 meters for distance. So that eliminates this one, and this one. And then displacement is the shortest distance between where he started and where he ends up. So if he goes 1,200 meters east, but then travels back 760 meters, what's the distance between where he winds up and his starting distance? That is 440 meters east of where he initially started, right? Because 1,200 minus 760 equals 440, and that is 440 meters east. Now we're getting into speed and velocity. So now we can answer how fast. Once we know how far an object moved and how much time it was in motion, we can calculate how fast it moved. And this question is measured in terms of speed or velocity. So if you look at the speedometer in a car, it will say, let's say 100 kilometers per hour. And if we go for 1 hour and drive, you will travel 100 kilometers per hour. Speed is a scalar quantity, so it includes the rate, but not which way you're going. Sometimes it's important to know how fast we're traveling and in what direction, especially if you want to change direction in a trip. And if you want speed plus a direction, that is velocity. Speed tells us how fast an object is moving. Velocity tells us how fast and in what direction. Speed. Speed is defined as the distance traveled divided by time. And this is speed equals distance divided by time. And under the SI, or International System of Units, distance is measured in meters, while time is measured in seconds. So the unit of speed is meters per second. Speed is also commonly seen in terms of kilometer per hour. And remember that speed is always positive. While driving, we sometimes go faster on a clear stretch of good road with little traffic and slow down on, those bad roads or where there's lots of cars. So at the end of the trip, if we want to know how fast we traveled overall, we calculate the average speed, and that's the total different distance covered in a given time divided by the total time. So here are a few ways to write that out. Average speed equals total distance divided by total time, or S equals the change in distance over the change in time. And this delta is a Greek letter, and anytime you see that in an equation, that just means change. Change in time. Now, velocity is the rate and direction in which an object changes its position. So, consider displacement as well as distance. Displacement is the change in position, and in terms of displacement and velocity, velocity is displacement divided by time. Since displacement is measured along the shortest path between 2 points, its magnitude is always less or equal to the distance traveled. Displacement is most commonly measured in meters per second, like speed. And to calculate the average velocity, you divide displacement by time. Often displacement in an unspecified direction is taken to be in the x direction. So mathematically, we define that as average velocity equals total displacement over time, or V equals change in x, displacement, over change in time. And again, a reminder, delta, Greek letter for change. Also notice that the vectors shown here are bolded symbols. And in problem solving, we're often focused on numerical values only. So in those cases, the values are not bolded. So keep that in mind. Okay, so here we go with an example. At a certain point during its launch from Cape Canaveral in Florida, a space shuttle traveled a distance of 2,500 meters at a distance of 500 meters per second. We'll calculate the time the space shuttle took to travel the distance. So we're given distance covered, 2,500 meters, speed, 500 meters per second. And we know that speed equals distance over time. So using algebra, you can solve for time. Time equals distance divided by speed. In this case, we just multiply time over here and then divided speed over here, okay? We have 2,500 meters divided by 500 meters per second. The meters cancel out, and then we're just given 5 seconds. Okay? Another example. A truck left point A and began traveling east. After 2 hours, it stopped at a gas station to refuel. The truck is now 146 kilometers from point A. What is the average velocity of the truck? So we're given the displacement, 146 kilometers from where it started, and the time, 2 hours. So we have average velocity equals displacement over time. 146 over 2, 73 kilometers per hour. Now we're given a lesson activity. And yeah. So I'll walk through them. A swimmer takes 45 seconds to complete a 100-meter lap. What's the average speed? So we're given 45 seconds. He's swimming 100 meters. So speed equals distance divided by time. 100 meters divided by 45 seconds. 2.22 meters per second. No direction needed. A race car completed a race in 150 minutes. Average speed was found to be 150 kilometers per hour. Was the total distance that the car has covered? Well, we're given the time, 150 minutes. 150 minutes is 2.5 hours. And we're also given the average speed, 150 kilometers per hour. So if average speed equals total distance divided by total time, you can solve for total distance. Average speed times time, we have 150 kilometers per hour times 2.5 hours, and that leaves you with 375 kilometers. Two cyclists start on a race between point A and D on two different routes. Cycle X takes the route passing through equidistant points A, B, C, D. So bam, bam, bam for cyclist one, or yeah, cyclist X. And then cyclist Y takes the AD route. That AD route has 546.41 meters. And then each of these points are 200 meters, 2, 4, 6. Both cyclists reach the end point in 30 seconds. Calculate the displacement and average velocities of cyclists X and Y. So they are both their displacement is 546.41 meters because they wind up in the same spot. The velocity for X is the displacement divided by time. So we have 546.41 divided by 30 seconds is 18.21 meters per second. And then we get the same thing for cyclist Y. Because velocity is displacement divided by time, they both have the same displacement. Both took 30 seconds, so we get the same velocity. So even though they traveled different distances in the same time interval, their velocities and displacements are the same. Because these are dealing with directions and where you wind up compared to where you started. Maggie participated in a race. She ran 100 meters west and turned back and ran to the starting line to complete the race. Maggie covered the entire distance in 40 seconds. What are her average speed and average velocity? So she ran 100 meters and then 100 meters in 40 seconds. 40 seconds time, total distance, 200 meters. If average speed is total distance divided by time, we have 200 meters divided by 40 seconds. We have 5 meters per second. Now to find velocity, we need to know the displacement. And because she started and ended at the same spot, her displacement is 0 Therefore, her velocity was 0. Average velocity, 0. Okay? Another question. Easy question. Speed. While loading a truck, trucks move 10 meters west from point A to point B in 5 seconds. 10 meters west in 5 seconds. Then it moves back in 5 seconds. The average speed is the total distance divided by the total time. So you have 10 meters, and then 10 meters divided by 10 seconds. So we have 20 divided by 10. That's an average speed of 2. So these answers are wrong. And then average velocity is 0 because he winds up in the same spot. Okay. Direction matters for velocity. Now we get into acceleration. That is, how fast is the velocity changing over time? And velocity is speed in a given direction, and average velocity is overall displacement over total time. But it doesn't tell you how fast your speed and direction changes. And this rate of velocity changing is acceleration. So when you're driving a car, if you press the accelerator, it goes faster. And how quickly the car picks up speed depends on how hard the driver presses the accelerator and what type of car it is too. So a car at rest has a velocity of 0 kilometers per hour. But when the driver steps on the accelerator, the car's velocity increases to 50 kilometers per hour after 10 seconds. So for every second, on average, the velocity of the car increases by 5 kilometers per hour. So this change in velocity per unit time is what physicists call acceleration. And acceleration, like velocity, is expressed in terms of both magnitude and direction and a vector quantity. So let's see how we can calculate it. Here's another visual acceleration. A equals change in velocity over time, or delta V over delta T, or final velocity minus initial velocity over change in time. And the unit of measure is meters per second, or meters per second squared. And acceleration can be negative or positive, and that tells you which direction the acceleration is going. So, assuming the car is traveling in a positive direction, both velocity and acceleration are positive. But if you brake, the acceleration is negative because you are changing, your change in velocity is negative, right? And we'll see that in a few more problems. Example 1, so you're starting out at 0 meters per second at rest. And you're on a straight road and you accelerate to 30 meters per second in 10 seconds. So we know that acceleration equals the change in velocity divided by the change in time. So we have a equals 30 minus 0 divided by 10 seconds. So we have 30 over 10 meters per second over seconds, or 3 meters per second squared. Here's an example that'll show you how acceleration can be negative. We have a van at a velocity of 20 meters per second moving to the east. But he has to brake, and he comes to a stop. So his velocity is 0 meters per second, and that happens within 5 seconds. So initial 20 meters per second, final velocity 0, time 5 seconds. So plug into this equation. We have a equals 0 minus 20 divided by 5, negative 20 over 5, negative 4 meters per second squared. Because the final velocity is less than the initial velocity, that is why acceleration is negative in this case. Then we're given more examples. Initial velocity 0, and then final velocity is 25 meters per second. All that takes place in 10 seconds. Just plug in to this equation, and you wind up with 2.5 meters per second squared. A rocket launched is subjected to a uniform acceleration of 100 meters per second squared. Determine the time needed to reach the final velocity of 1,000 meters per second. So, given this equation, plug in what you know. If you're looking for t, get t by itself. Then just plug in your final velocity of 1,000 minus the initial 0 all over the acceleration that we're given, which is 100 meters per second squared up here. And then you get time equals 10 seconds. And question 2, you are given a simulation and it tells you what to do step by step. So I will let you have fun with that. And I'll move on to the summary. So remember the horse racing example before. Dave and his physicist friend were right about the horse race. They were using different but accurate terms to describe the same event. Average speed of Dave's horse was 12.5 meters per second. And because the horse started and stopped at the same point, his displacement was 0, so his average velocity was also 0. Distance and displacement answer how far. Distance just tells you the magnitude. Displacement tells you the direction as well as how far away from the initial point you are. And it's the shortest path between an object's initial and final position. Speed and velocity. Speed is distance over time. Velocity is displacement over time. So velocity tells us how fast and in what direction something is moving. Then we have acceleration, which is how fast the speed and direction is changing as well. So how fast is velocity changing? And we are given this equation. Change in velocity is delta v over delta t, or change in v over change in t. Okay, so hopefully those terms are easier to understand, and you're kind of getting a feel for how to solve these more mathy equations in science. So we will move on with motion, and I hope you have a great day, and I will see you later. Bye-bye.